Deep beneath the countryside that runs along the border between Switzerland and France, there is a tunnel. It is not a dramatic tunnel. It does not look like the kind of place where history gets made. The walls are lined with cables and pipes, and the gentle hum of machinery that runs continuously, day and night, for months at a stretch. The people who work there carry coffee in paper cups, and wear ordinary clothes and talk about ordinary things: football, weekend plans, the particular frustration of software that takes too long to process data. They are ordinary people, and for most of the day the work they do feels ordinary too. But then the beam comes on, and something extraordinary begins. Before we continue, if you're curious about the universe, obsessed with the unknown, and want to see the latest discoveries before everyone else, press the like, subscribe, hype and comment where in the world you're listening from. The machine buried in that tunnel is called the Large Hadron Collider, and it is the most complicated object that human beings have ever built. It stretches for 17 miles in a perfect underground circle, and inside it, particles smaller than anything you can imagine are accelerated to speeds that approach, but never quite reach, the speed of light. They travel in opposite directions around that circle, guided by superconducting magnets chilled to temperatures colder than the emptiness between stars. And then, at precise points along the ring, they are made to collide. Not gently, not carefully, with a violence that briefly recreates the conditions that existed in the first fractions of a second after the universe began. What spills out of those collisions is information. Cascades of particles, trails of energy, signatures that the detectors arranged around the collision points capture and record in real time. The data pours in at rates that would overwhelm most computer systems, and teams of physicists around the world spend months, sometimes years, processing and interpreting what the machine has seen. Most of the time, what they find is exactly what they expected, and for a long time, that was deeply reassuring. It meant that the picture of reality that physics had been building for the better part of a century was accurate. It meant the map matched the territory, but then, slowly, quietly, something began to change. Not in the dramatic way that movies would have you imagine. There was no single moment of revelation, no alarm sounding, no scientist dropping their coffee and staring wide-eyed at a screen. It happened the way most real scientific discoveries happen, gradually, through accumulation, through the patient examination of numbers that were almost right but not quite, through the slow realization that the discrepancies were not going away, they were growing, and what they were suggesting, if you followed the logic carefully and without letting yourself look away, was something that even the most experienced physicists found genuinely strange to sit with. The rulebook of reality, the framework that physics had built to describe every particle and every force that exists, was incomplete. Not wrong exactly, incomplete. Like a map that is accurate for most of the territory but simply goes blank at the edges. With a quiet note in the margin that says something more is here, we just do not know what it is. That framework has a name. It is called the Standard Model of Particle Physics, and understanding why it matters, and why the cracks in it matter even more, is where this story truly begins. Not with a bang, not with a crisis, but with the slow and beautiful work of human beings trying to understand the smallest possible things, and discovering, in the process, that those smallest things hold the answers to the largest questions anyone has ever asked. Think for a moment about what matter actually is. Not the philosophical version of the question, but the physical one. If you take any object, anything at all, a stone, a leaf, a drop of water, and you break it down into its smallest possible pieces, what do you find? For most of human history, the answer was atoms, tiny, indivisible particles of matter, each one specific to a particular element, each one the building block of everything larger. That model held for centuries. It felt complete. It felt final. The ancient Greeks who first proposed the atom as the irreducible unit of matter would not have been entirely wrong, just incomplete in the same way that all of physics has been incomplete at every stage of its development. But atoms are not indivisible. Inside them, there are smaller things. Protons and neutrons packed into a tiny nucleus, with electrons moving around the outside in patterns that determine how the atom behaves and what it can bond with and what kind of chemistry it can participate in. And inside the protons and neutrons, smaller things still, quarks, were bound together by a force so powerful that it has never been observed to release a single quark into the open world. Not because the force becomes stronger at long distances, which is exactly what it does, getting tighter the further you try to pull quarks apart, but not in the intuitive way of an ordinary spring. More like a rubber band that stretches and builds tension, and then, just when you think you might finally be able to separate the quarks, snaps back with enough energy to create a new pair of quarks from the vacuum itself. And surrounding and threading through all of this, fields, invisible, omnipresent, stretching across all of space, the medium through which forces travel and through which particles acquire their properties. The electromagnetic field fills every corner of the universe. The Higgs field, as once a theoretical prediction and now a confirmed physical reality, does the same. These fields are not metaphors. They are real physical entities, as real as the particles that exist as their ripples, as real as the forces that their fluctuations carry. The Standard Model is the mathematical description of all of this. It describes the quarks and the electrons and the neutrinos and the photons and the gluons, and a whole collection of other particles, each one playing a specific role in the structure of matter and energy. It describes the forces that connect them, the electromagnetic force that governs how charged particles interact, the strong force that holds quarks together inside protons and neutrons, and the weak force that governs certain kinds of radioactive decay. It was built over decades by hundreds of physicists working across multiple countries, combining experimental data with theoretical insight in a process that is slow and collaborative, and occasionally punctuated by moments of genuine wonder. And it works. It works better than almost any other scientific theory in history. The predictions it makes about how particles will behave have been tested to extraordinary precision and have come out correct again and again. In 2012, the Large Hadron Collider found the Higgs boson, the last particle that the Standard Model predicted but had not yet been directly observed. It was a triumph. It was the culmination of decades of effort and billions of dollars in investment and the careers of thousands of physicists. It was, for a brief and beautiful moment, the feeling that the picture was complete. And then the measurements started coming back wrong. Not dramatically wrong, not wrong in the way that would suggest the entire framework was broken. Wrong in the way that a very precise instrument sometimes gives you a number that is just slightly, persistently, reproducibly off from what every calculation says it should be. And in physics, that kind of wrongness is not an annoyance. It is a signal. It is the universe nudging you towards something you have not yet understood. The first of those nudges arrived through the measurement of a particle called the W boson. It is not a famous particle. Most people have never heard of it, but it plays a fundamental role in the structure of matter. It is one of the carriers of the weak force, the force responsible for certain kinds of radioactive transformation, the force that allows a neutron to become a proton and release an electron in the process. Without the W boson, the sun would not shine. Without the W boson, the nuclear reactions that power stars and forge the heavy elements that make up planets and people would not proceed. It is quiet and invisible and absolutely essential, and its mass came out wrong, not by much, by a tiny fraction of a percent. But the instruments making the measurement were so precise that a tiny fraction of a percent was impossible to dismiss. The discrepancy between the measured mass and the predicted mass was larger than any reasonable accounting for experimental error could explain. It sat there in the data, calm and stubborn, and quietly alarming, suggesting that the equation describing the W boson was missing a term, that something was adding weight to the particle that the Standard Model had not accounted for, something hidden, something present but invisible, leaving a fingerprint in the mass of a particle we thought we understood completely. The scientists who found this result were careful. They published it. They were challenged. Others looked at the same problem with different experiments and found different, somewhat smaller discrepancies. The scientific community, as it always does, began the slow process of working out which measurement was more trustworthy and what the disagreement might mean. That process is still ongoing. But the important thing, the thing that matters for this story, is not the specific number, is what the existence of even a small reproducible discrepancy implies. It implies that the map is not quite right, that there is territory at the edges of the Standard Model that the model itself cannot describe. And once you know that, once you hold that quiet fact in your mind and let it settle, the questions that follow are not small ones. What is missing? What is the standard model not seeing? And if the framework that describes every particle and every force we know of is incomplete, what does it say about the nature of reality itself? Those are the questions this story's about. And they are not frightening questions, not really, not in the way that darkness is frightening. They are more like the feeling you get when you're reading a very good book and you realize somewhere around the middle that the story is far larger than you thought it was, that there are layers you have not yet reached, that the ending is going to change how you see the beginning. The crack in the wall of the standard model is not the end of physics, it is the beginning of something else. Something that the instruments buried in the Swiss countryside are only just beginning to reveal. And to understand what that something is, you have to go back, much further back, to a moment before the crack appeared, before the machine was built, before the equations were written, to the question that started all of this in the first place. What is the universe made of? Not in terms of particles, not in terms of forces, but at the deepest level, at the level that underlies everything else. What is the fabric of reality? And why does it have the particular shape that it does? That question has been sitting quietly at the centre of physics for a long time. The standard model gets you part of the way toward an answer, but not all the way. It tells you what the particles are and how they interact, but it does not tell you why those particular particles exist and not others. It does not tell you why the forces have the strengths they do. It does not tell you where gravity fits in, because gravity, the force that shapes everything, at the largest scales, the force that holds galaxies together and bends light and pulls you toward the Earth, does not appear in the standard model at all. Not because physicists forgot to include it, because it does not fit. The mathematics of gravity and the mathematics of the other three forces simply refuse to combine into a single coherent picture. They are two different descriptions of the same universe that cannot be reconciled, and every attempt to force them together produces mathematical absurdities, infinities that signal a breakdown of the framework rather than a physical prediction. That gap between the theory of the very large and the theory of the very small is perhaps the deepest open problem in all of physics, and it is the shadow that falls over everything the Large Hadron Collider has been discovering. Because every anomaly it finds, every discrepancy between measurement and prediction, is a clue. Not a definitive answer, not yet, but a clue. A whisper from the universe about where the next layer of understanding might be found. And in the late hours of the night, when the collider is running and the data is flowing and the machines are humming in their cold underground ring, that whisper feels very close. Not alarming, just present. A quiet reminder that the universe is more than the part of it we can currently see, and that the work of understanding it is far from over. This is where we begin. Not at the end of something, but at the beginning of a question so large it contains smaller questions the way the night sky contains stars, countless, layered, each one a little further away than the last, each one requiring its own patient looking. The earliest experiments in particle physics were almost touching by comparison to what is happening in Switzerland today. In the 1890s, J.J. Thomson discovered the electron using a glass tube, a vacuum pump, and an electrical discharge. In the 1910s, Ernest Rutherford discovered the atomic nucleus by firing alpha particles at a thin gold foil and noticing that a small fraction of them bounced backward, something he compared to firing artillery shells at tissue paper and having them come back and hit you. These experiments were small enough to fit in a room. The people doing them could build the apparatus themselves, could adjust and modify it in an afternoon, could feel the texture of the science with their hands. The Large Hadron Collider is not like that. It is 10,000 people across more than 100 countries. It is a machine that took decades to design and a decade to build, and that will run for decades more. It is collaboration on a scale that the human species has achieved only a handful of times, and each time has required some combination of collective ambition and shared curiosity, and the particular kind of trust that comes from knowing that your colleagues care as much about getting it right as you do. The LHC is a monument to what the species can do when it asks a sufficiently large question with sufficient seriousness. And the question it is asking, what is the fundamental structure of reality, is one that does not have a deadline and does not have a guaranteed answer within any particular time frame. The physicists who work at the LHC are comfortable with this. They have made peace with the possibility that the new physics they are looking for may remain just out of reach for years or decades more, that the machine they have devoted their careers to may not find the breakthrough they are hoping for, that the breakthrough may come instead from a direction they did not anticipate. From a theoretical insight or a technological development or an observational discovery that makes the question answerable in a completely different way than any of them currently imagines. This comfort with open-endedness, with the long game of understanding, is one of the most admirable qualities of the scientific community, and one of the most necessary ones given the nature of the problems being pursued. The crack in the wall is real. The anomalies are real. The gap between the standard model and the full theory of nature is real, and the work of understanding it is the most important scientific work of our time, slow and patient and occasionally punctuated by discoveries that change how we see everything. Conducted by thousands of people in an underground ring in Switzerland, and in observatories on mountaintops and in theoretical physics departments around the world, all of them pointing their instruments and their minds at the same beautiful and frustrating and endlessly interesting question: what is the universe? And in the quiet of the night, with the beam running and the data flowing, the question has never felt more alive. If you wanted to understand the universe, and you had the patience to sit with the mathematics long enough, you would eventually arrive at a set of equations that describe, with extraordinary precision, everything that ordinary matter does. They fill textbooks. They have won more Nobel Prizes than any other framework in the history of science. They describe not just what things are made of, but how they behave, how they transform, how they communicate across empty space. And they are, in the quiet and humbling sense of the word, beautiful. Not decoratively beautiful in the way a painting might be, but structurally beautiful, the way a proof is beautiful, the way a mechanism is beautiful when all its parts fit together with perfect economy, and nothing is wasted. The standard model grew slowly, the way most great scientific structures grow, not from a single insight but from the accumulated work of generations. It is a collaborative monument. Its foundations were laid in the early decades of the 20th century, when physicists were still coming to terms with the strange new world of quantum mechanics, the discovery that at the smallest scales, reality does not behave the way the everyday world does. Things do not have definite positions until they are observed. Particles can pass through barriers they should not be able to pass through. Two particles that have interacted can remain connected across any distance, so that measuring one instantly tells you something about the other. Energy comes in discrete packets, not continuous flows. The universe, at its smallest scales, is lumpy and probabilistic, and refuses to commit to a single definite state until something forces it to. These were not intuitive ideas. They were not the kind of ideas that fit easily into the mental categories that human beings naturally carry around. They required a different kind of thinking, a willingness to hold contradictions gently, and let the mathematics lead even when the physical picture refused to come into focus. And the physicists of that era, Heisenberg and Schrödinger and Dirac and Pauli and Bohr and many others, did exactly that. They followed the equations, even when the equations were saying things that seemed impossible, and they found that the equations were right, that the impossible was not actually impossible, that the universe at the quantum level was simply different from the universe at the human level, obeying the same ultimate laws but expressing them in ways that nothing in ordinary experience had prepared anyone to expect. Quantum mechanics gave birth to quantum field theory, the deeper framework from which the standard model eventually emerged. In quantum field theory, particles are not little balls flying through empty space. They are excitations of fields. Imagine a calm ocean. The ocean itself is the field, stretching across all of space. A wave on that ocean is a particle. The Higgs field, the electromagnetic field, the quark fields, they all exist everywhere simultaneously, filling all of space at all times, and the particles we observe are ripples in those fields, brief concentrations of energy that behave in certain ways like the objects we are used to thinking of as matter. This picture is strange. It does not match anything in ordinary experience, and yet it is phenomenally successful. The precision with which quantum field theory predicts the behavior of electrons, for example, is almost beyond comprehension. Certain quantities have been measured and calculated to more than 10 decimal places, and the measurement and the calculation agree. That level of agreement is not luck, it is not coincidence. It is the signature of a theory that is genuinely describing something real about the nature of things. When a description matches reality to 10 decimal places, the description is not merely useful. It is true in the deepest sense that science can offer. The Standard Model takes this framework and populates it. It identifies the fundamental fields, the ones whose ripples we call particles, and it describes the interactions between them through a mathematical structure called gauge symmetry. Gauge symmetry is not easy to explain in simple terms, but the essential idea is that the laws of physics should look the same regardless of certain kinds of internal transformations in the mathematical description. It is a constraint, a kind of consistency requirement, and what makes it remarkable is that insisting on that consistency is what forces the forces into existence. The electromagnetic force, the strong force, the weak force, they all emerge from the requirement that the mathematics remain consistent when you apply these internal transformations. The forces are not added by hand, they are demanded by the structure. They are necessary, not arbitrary. This is one of those moments in science where the elegance of the mathematics goes beyond mere aesthetics and starts to feel like evidence. When a framework this beautiful makes predictions that turn out to be this accurate, it is hard not to feel that it is capturing something genuinely deep about the structure of reality. Not just describing it, but touching the underlying logic that makes things the way they are. The famous physicist Eugene Wigner wrote an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, and the Standard Model is perhaps the clearest example of what he was pointing at. There is no obvious reason why the requirement of gauge symmetry should produce the forces of nature, and yet it does. Perfectly. And for decades that feeling was justified by results. Prediction after prediction was confirmed. The W and Z bosons, particles that carry the weak force, were predicted mathematically before any experiment had found them, and then found exactly where the equations said they would be, with the masses the theory predicted behaving precisely as the mathematics required. The top quark, heavier than any other fundamental particle, was predicted and then discovered. The entire zoo of particles that the Standard Model describes, quarks of 6 different types, leptons including the electron and its heavier cousins, neutrinos that pass through ordinary matter almost without interaction, gauge bosons carrying the forces, all of them appeared in experiments, all of them with the masses and behaviours the equations anticipated. Then, in 2012, the Higgs boson, the last piece, the particle associated with the field that gives all the others their mass. Its discovery was genuinely historic. Physicists who had spent their careers working toward that moment described crying in the control room when the statistical significance of the signal crossed the threshold for a confirmed discovery. The observation that the Higgs boson had been found was made first at the Large Hadron Collider. By 2 independent experimental collaborations, each with thousands of members, each using different detector technologies, each arriving at the same conclusion from their own data. That kind of independent confirmation, from 2 separate experiments using different methods, is the gold standard of particle physics. It felt like the end of a very long journey. It felt like completion. But here is the quiet and important thing about completion in science. It never actually arrives. What looks like the end of one story is always the beginning of another, and the Higgs boson, rather than closing the book on the Standard Model, opened a new set of questions that turned out to be even more difficult than the ones it answered. The mass of the Higgs boson, when measured precisely, came out at around 125 times the mass of a proton. That is a specific number, and like all specific numbers in physics, it raises the question of why it is that number, and not some other. The answer, according to the equations of the Standard Model, depends on contributions from every other particle in the theory. Those contributions can be enormous. The quantum corrections to the Higgs mass, the mathematical terms that arise from its interactions with other fields, are in principle astronomically large, far larger than the observed mass. For the measured mass to come out at the relatively modest value that experiments find, those enormous contributions must cancel each other almost exactly. The positive contributions from some particles must nearly perfectly cancel the negative contributions from others, leaving only the small remainder that corresponds to what the LHC measured. Almost exactly is the important phrase. The cancellation is not perfect. It does not need to be perfect, but it needs to be extraordinarily precise. The degree of fine-tuning required, the degree to which the various contributions to the Higgs mass must be balanced against each other to produce the observed result, is so extreme that most physicists find it deeply uncomfortable, not impossible, not forbidden by any law of physics, just the kind of improbable that makes you think you are missing something, the kind of improbable that suggests a deeper explanation is waiting to be found, a natural mechanism that would make the cancellation automatic rather than accidental. This problem has a name. It is called the hierarchy problem, or sometimes the naturalness problem. And it is not a new concern. It has been sitting in the back of physics for decades, a quiet source of unease among people who think carefully about the structure of the theory. The standard model requires this unlikely balance, this near-miraculous cancellation, and it offers no explanation for why that cancellation should occur. It just happens, in the mathematics, to come out right. And that feels, to a careful mind, like the kind of coincidence that usually turns out not to be a coincidence at all. The history of physics is full of apparent coincidences that turned out, when understood more deeply, to be necessary consequences of deeper principles. And the hierarchy problem feels like that, like a coincidence that is secretly a clue. The most popular proposed solution to the hierarchy problem. Before the Higgs boson was discovered, and in the years leading up to its discovery, was a framework called supersymmetry. The idea is elegant. Supersymmetry proposes that for every particle in the standard model, there exists a partner particle with different spin but otherwise closely related properties. These partners, called superpartners, would contribute to the quantum corrections of the Higgs mass in a way that naturally cancels the contributions from the ordinary particles without requiring extraordinary fine-tuning. The cancellation would be built into the structure of the theory, demanded by the symmetry, rather than achieved by accident. Nature would be natural again. Supersymmetry also, as a bonus, provides a natural candidate for dark matter. The lightest superpartner, if supersymmetry is correct, would be stable and would interact only weakly with ordinary matter, making it invisible to ordinary detectors. It would be exactly the kind of particle that could account for the invisible mass that astronomers observe affecting the motion of galaxies without producing any light. And supersymmetry also helps with the unification of forces, making the coupling constants of the three standard model forces converge to a single value at very high energies in a way that suggests they become a single unified force in that regime. Three problems addressed by one elegant idea. It was, for a generation of physicists, irresistibly compelling. The Large Hadron Collider was built, in part, to look for supersymmetric particles. If they existed with the masses that the most natural versions of supersymmetry predicted, the collider should have found them within the first few years of operation. The signatures would be characteristic and recognizable. It has not found them. It has looked carefully, with increasingly sophisticated detectors and increasingly large datasets, and the characteristic signature of supersymmetric particle production has not appeared. The absence of superpartners at the energies the LHC can probe does not rule out supersymmetry entirely, but it pushes the hypothetical partner particles to higher and higher masses, making the theory less natural with every passing year. The solution that was supposed to solve the naturalness problem is itself starting to look unnatural. It is a deeply ironic situation, and one that the theoretical community is still working through. This is where physics stood when the anomalies began arriving. The Higgs boson had been found. The standard model was complete, in the sense of having all its predicted pieces confirmed, but the hierarchy problem remained unsolved. Supersymmetry, the leading candidate for a solution, was looking increasingly constrained. Gravity still refused to fit into the quantum framework, and then the measurements started coming back slightly wrong, in ways that no known mechanism could explain, in ways that were small enough to be possibly statistical, but persistent enough to refuse to disappear, in ways that pointed quietly and consistently towards something that the current framework could not see. The picture that emerged was not one of collapse. The standard model did not fail. It has not failed. It continues to make accurate predictions about the vast majority of what the LHC observes. But the edges have become visible. The places where the map goes blank, the regions where the theory falls silent and offers no guidance, have become more clearly defined. And what sits in those blank regions, what fills the silence at the edge of the map, is the most interesting question in physics right now. One of the most instructive aspects of the standard model's development is how long it took to appreciate that something was missing. For years after the model was assembled, The particle physics community celebrated its success and focused on its predictions. The hierarchy problem was known, but the preferred theoretical response was optimism. Supersymmetry would solve it. The right extension of the model would be found. The large colliders being planned would discover the new particles and the picture would snap into focus. The confidence was understandable. The model had been so successful in every previous test that it was natural to assume the next challenge would also yield to the same kind of theoretical creativity that had produced such elegance before. What the LHC found instead was not new physics at the expected scale, but a Higgs boson with properties that were unsettlingly close to the standard model prediction, without the accompanying new particles that would have explained why the Higgs mass is what it is. The boson was found. The explanation for its mass was not. And this combination, a confirmed prediction without the predicted explanation, has forced the theoretical community into a more careful examination of what it means for a theory to be natural and whether naturalness. The expectation that parameters should be of an order 1 unless there is a reason for them to be small is the right guide for theoretical progress at this frontier. The naturalness debate has become one of the most active in theoretical physics. On one side are those who maintain that the hierarchy problem is real and that its solution must exist, that the current failure to find it reflects the limited energy reach of the LHC rather than the absence of a solution. On the other side are those who argue that naturalness may not be the right criterion, that the landscape of string theory makes apparent fine-tuning common and perhaps even expected, that the selection effects that come from living in a universe hospitable to life can account for the seemingly improbable values of the standard model parameters. Between these poles are many shades of opinion, and the debate shows no signs of resolution by pure argument. Only data can settle it, and the data from the LHC and its successors will be the judge. What is clear, regardless of one side, the naturalists versus the landscape observers, is that the standard model is the beginning of the story, not its end. Its parameters, its particles, its forces are not the bedrock of reality but the visible expression of something deeper. And the crack in its wall, the persistent small wrongnesses in the most precise measurements, the blank regions where its explanations give out, are the places where the deeper structure is beginning to show through. The story of what that deeper structure is the story that this entire investigation has been building toward, one careful measurement at a time. There is a question that physics has been quietly failing to answer for about a century, and it is one of the strangest questions in all of science, not because it is abstract, but because it is so alarmingly concrete. The question is this: what does empty space weigh? And the answer that physics gives, when you work through the calculations carefully and honestly, is a number that disagrees with observation by the largest factor ever recorded in the history of scientific measurement. Not a little off, not a factor of 2 or 10 or 1,000, but a factor so enormous that the very concept of a factor struggles to contain it. It sounds almost silly at first. Empty space, by definition, should contain nothing. And nothing, it seems reasonable to assume, should weigh nothing. But quantum mechanics, the framework that describes the behavior of matter and energy at the smallest scales, says otherwise. It says that empty space is not actually empty. It is filled, at every point, with the ceaseless fluctuation of quantum fields. Pairs of particles and antiparticles continuously flickering into existence and vanishing again before they can be directly detected. A permanent, invisible fizzing at the base of reality that never stops, not in the coldest, emptiest corner of deep space, not in the most carefully prepared laboratory vacuum on Earth. The vacuum is alive with activity that no instrument can directly observe, but that the mathematics insists is real. These fluctuations carry energy, and energy, according to Einstein's famous equation relating mass and energy, is equivalent to mass, which means that empty space, quantum mechanically speaking, has a weight, a vacuum energy, a density of energy spread evenly through all of space, filling every point in the universe at every moment in time. The vacuum is not nothing. The vacuum is something. It is the most fundamental something that exists. The problem is that when you calculate what that vacuum energy should be, based on what quantum field theory says about the fluctuations in each field, you get a number. And then when you compare that number to the actual energy density of empty space, measured through astronomical observations of how the universe is expanding, you find a discrepancy. not a small discrepancy. A discrepancy of somewhere around 10 to the power of 120, one followed by 120 zeros. The theoretical prediction and the observed reality differ by the largest factor in the history of scientific measurement, by so much that it makes the number almost impossible to process emotionally or intellectually. This problem is called the cosmological constant problem, or sometimes just the vacuum catastrophe, and that second name tells you something about how physicists feel about it, even after decades of sitting with it. It is not a puzzle that has been filed away as interesting but unimportant. It is a direct confrontation between the two most successful frameworks in the history of physics, quantum mechanics, and general relativity, and the confrontation produces a result that neither framework can explain. The vacuum, which general relativity treats as potentially having an energy density, has one, but quantum mechanics predicts that density to be so large that the universe would not exist in anything like its current form if the prediction were correct. Either the calculation is profoundly wrong in some way we do not understand, or something is cancelling the vacuum energy to extraordinary precision for reasons we have not identified, or the relationship between quantum mechanics and space-time curvature is something altogether different from what both theories currently suggest. What does metastability mean for the vacuum specifically? And why do physicists think our vacuum might be in this condition? The answer connects to the precise measurement of the Higgs boson's mass. When theorists trace the behaviour of the Higgs field to very high energies, they find that the self-coupling of the field, the parameter that determines the shape of the Higgs potential, runs with energy in a specific way. And for the particular values of the Higgs mass and the top quark mass that experiments measure, the self-coupling becomes very small and potentially negative at energies far above what any collider has reached. If it goes negative, the current minimum of the Higgs potential, the field configuration that gives particles the masses we observe, is no longer the true minimum. There is a deeper minimum, a different lower energy configuration. The transition from our current vacuum to that deeper configuration is the process called vacuum decay. It would begin at a single point in space where the Higgs field spontaneously tunneled from the current configuration to the lower one. A bubble would form, a tiny region where the laws of physics are different, where the Higgs field has settled into its true minimum rather than the metastable one we currently occupy, and that bubble would grow rapidly. Because inside the bubble, the energy is lower, and the universe always tends toward lower energy configurations. The bubble wall would expand outward at the speed of light, converting everything it passed through from the familiar universe to whatever the lower vacuum configuration supports. This does not mean what you might fear it means. The calculations suggest the probability of this happening anywhere in the observable universe within any timescale relevant to human civilization, or even relevant to the lifetime of the Sun, is extraordinarily small. The metastable state, if that is indeed what we occupy, is stable on cosmological timescales that dwarf anything humanity will ever care about practically. So this is not a practical concern in any sense that should affect how you live your life, or what you plan for tomorrow. But the possibility matters profoundly in a different sense. It matters because it tells you something deep about the structure of the universe. It tells you that the ground state of the most fundamental field we know of, the field that gives all particles their mass, may not be the deepest available ground state. We may be living in a metastable configuration, a quantum state that has persisted for billions of years, not because it is the most stable possible state, but because the transition rate to the more stable one is extremely small, and that raises a question that the standard model simply cannot answer. Why this vacuum? Why did the universe settle into this particular metastable configuration after the Big Bang, and not a different one? Is there a mechanism that selected it? Or is it an accident? The cosmic equivalent of a ball that happened to roll into a shallow bowl rather than continuing to roll until it reached the valley floor? These questions do not have answers yet. But the fact that they are being asked, the fact that the measurements that come out of experiments are precise enough to raise them, is itself significant. It means we are beginning to probe the structure of the vacuum itself, to peer into the nature of the ground floor of reality. And what we find there is not the featureless, empty nothing that intuition would suggest. It is a landscape, a complex, structured, possibly vast landscape of different possible vacua, each one corresponding to a different set of physical laws, a different universe with different particles and different forces and different possibilities for complexity. The vacuum is not the absence of physics, It is the source of physics, and if it is more complex than we thought, if it has depth and structure, and the latent possibility of transformation, then everything built on top of it, everything we see and measure and call reality, is in some sense a construction resting on a very peculiar and very interesting foundation. There is something almost meditative about this idea, if you let it settle slowly rather than grabbing it quickly. The universe is not a collection of things floating in an empty container. The container itself is active, it has energy, it has history, it made a choice, in the first moments after the Big Bang, about which vacuum to occupy, and that choice is the foundation on which everything you have ever known, every atom, every star, every thought you have ever had, is built. And the machine in Switzerland is, among other things, trying to understand that choice. Every structure has a skeleton, buildings have steel frames, bodies have bones, mountains have the geology beneath them, the ancient compressed rock that holds everything up. And the universe, it turns out, has a skeleton too. One that cannot be seen, one that does not interact with light in any way, one that has been shaping the cosmos for as long as the cosmos has existed, quietly and invisibly, pulling matter into the shapes we observe without ever leaving a trace of itself in any form of radiation that our instruments can directly detect. The skeleton of the universe is called dark matter, and its existence is one of the most secure results in all of modern science, confirmed by multiple independent lines of evidence across decades of observation, and one of the deepest mysteries because no one has any idea what it actually is. Astronomers began noticing its effects in the 1930s when Fritz Zwicky measured the velocities of galaxies within a large cluster and found that they were moving far too fast. The gravity of all the visible matter in the cluster, all the stars and gas and dust, was not nearly strong enough to hold the cluster together at those velocities. By all rights, the galaxies should have flown apart long ago, but they had not. Something was holding them, something with mass, something exerting gravitational pull, something that was simply not visible. As Zwicky's observation was dismissed at the time as probably an error, an artifact of some misunderstanding. But subsequent decades brought more evidence, from different directions, using different methods, arriving at the same conclusion. The rotation curves of spiral galaxies were perhaps the most compelling. When astronomers measured how fast stars in a galaxy were orbiting around the galactic centre, they expected the rotation speed to decrease with distance from the centre, the way planets in the outer solar system orbit more slowly than those in the inner. Instead, the rotation curves stayed roughly flat. Stars in the outer regions of galaxies were orbiting at speeds that the gravity of the visible matter could not account for. Something additional was providing gravity, something extended far beyond the visible disk of the galaxy, forming a large, roughly spherical halo of invisible mass surrounding each galaxy, the dark matter halo. Gravitational lensing provided independent confirmation. When light from a distant galaxy passes near a massive object, the object's gravity bends the light's path, distorting the apparent shape of the distant galaxy. The amount of distortion depends on the mass of the intervening object. Astronomers mapping these distortions in galaxy clusters found that the total mass required to produce the observed lensing was far greater than the mass of the visible matter. The dark matter was there, in the lensing signal, massive and invisible. The cosmic microwave background, the afterglow of the Big Bang, provided yet another line of evidence. The pattern of temperature fluctuations in this background radiation, measured with extraordinary precision by satellites, encodes information about the composition of the early universe. The precise pattern is sensitive to the ratio of ordinary matter to dark matter, and the fit to the observations requires dark matter to be present in roughly 5 times the abundance of ordinary matter. The evidence is built into the oldest light in the universe. All of these observations, from galaxy rotation curves to gravitational lensing to the cosmic microwave background, point to the same conclusion. The universe contains more mass than its visible components account for, about 5 times more. And that extra mass, the dark matter, is not made of protons and neutrons. It is not made of any particle in the standard model. Whatever it is something genuinely new. The Large Hadron Collider was designed, among other things, to find dark matter. The leading hypothesis before the LHC began operating was that dark matter consists of particles called WIMPs, weakly interacting massive particles. These would be particles with mass in roughly the same range as the known particles of the Standard Model, but interacting with ordinary matter only through the weak force and gravity, making them invisible to electromagnetic detection. If WIMPs exist with the right masses and interaction strengths, the LHC should be able to produce them in high-energy collisions, and they would leave a characteristic signature in the detectors, missing energy and momentum, the physics equivalent of suddenly discovering that some of what you put into a collision has not come back out on the other side. The LHC has not found WIMPs. Not at any of the masses where they were most expected. Not with any of the interaction strengths that the most natural WIMP models predict. The detectors are extraordinarily sensitive, the datasets are enormous, and the silence, the absence of the characteristic missing energy signature that WIMP production would produce, is itself a measurement. A precise measurement of where WIMPs are not. The regions of mass and interaction strength that have been ruled out keep expanding, and the space where WIMPs could still exist gets smaller with each new analysis. Some of those alternative possibilities are fascinatingly strange. Axions, particles originally proposed not to explain dark matter, but to solve a completely separate problem in the Standard Model, turn out to be excellent dark matter candidates. They are extraordinarily light, as billions of times lighter than the electron, and they interact with ordinary matter so weakly that they pass through everything without leaving a trace. Experiments searching for axions use carefully designed cavities where the tiny coupling between axions and photons could in principle produce a detectable signal. The searchers are pushing into increasingly sensitive regimes, but no axion has yet been found. The search continues. Then there is dark energy, which is stranger still. Dark matter is at least something, some form of matter with mass and gravitational effects. Dark energy is something else entirely. It is not matter. It is not radiation. It is apparently a property of space itself, an energy density inherent in the vacuum that does not dilute as the universe expands, that does not cluster around matter, that simply exists, everywhere, at all times, with a constant density pushing space apart. And it is responsible for one of the most surprising discoveries of the late 20th century, the discovery that the expansion of the universe is not slowing down, as the gravity of matter would cause it to do, but accelerating. This acceleration, confirmed in 1998, and now one of the most well-established results in cosmology, requires something that acts against gravity on cosmological scales. Dark energy is the name we give to whatever that something is. Its measured value, the density of this mysterious energy of space, is extraordinarily small but non-zero, small enough that it has negligible effects on the scales of stars or galaxies, but large enough that when integrated over the immense volumes of intergalactic space, it dominates the total energy budget of the universe. 68% of everything is dark energy, and we have no idea what it is. The 95% of the universe that is dark matter and dark energy is the most eloquent possible statement of where physics stands right now. We have a framework, the Standard Model, that describes with extraordinary precision the 5% we can see, and we are reaching, with every instrument at our disposal, toward the 95% we cannot. The machine in Switzerland is reaching from one direction. The telescopes and satellites and gravitational detectors are reaching from another. And the distance between the reaching instruments and the thing they are reaching for is one of the great measurement challenges in the history of science. There is a particular quality to the search for dark matter that sets it apart from most scientific investigations. In most experiments, you at least know what you are looking for. You have a theoretical prediction for a particle with specific mass and specific interaction strengths, and you build a detector sensitive to those specific properties, and you look. The search for dark matter is different because you know the effect, the extra gravity, the missing mass, the gravitational lensing, but you do not know the cause. The particle responsible could be almost anything that has mass and does not interact electromagnetically. The space of possibilities is genuinely enormous, and different experimental approaches are sensitive to different corners of that space. Underground detectors, deep beneath mountains or in old mines, look for the tiny recoil that a dark matter particle would produce when it occasionally scatters off an ordinary atomic nucleus. The underground environment is essential because it shields the detectors from cosmic rays and other backgrounds that would otherwise overwhelm the tiny signal. These detectors are made of ultra-pure materials, crystals of germanium or silicon or liquid noble gases like xenon or argon, cooled to temperatures near absolute zero so that even the tiniest energy deposit from a dark matter particle scattering produces a detectable signal. They have been running for years, getting progressively more sensitive, pushing into lower and lower interaction cross-sections, finding nothing. The null results are themselves informative. They rule out large regions of the WIMP parameter space. But the absence of a signal means only that dark matter does not interact with ordinary matter at the rate or in the way those specific detectors were sensitive to. It does not mean dark matter is not there. Cosmological observations provide a completely different handle on dark matter properties. The pattern of galaxies in the large-scale structure of the universe, the way galaxies cluster on different scales, the detailed shape of the fluctuations in the cosmic microwave background, all of these are sensitive to the properties of dark matter. In particular, they are sensitive to how fast dark matter was moving in the early universe, because fast-moving dark matter would have streamed away from potential wells and suppressed the formation of small-scale structure. The observations show that dark matter is cold, meaning it was moving slowly compared to the speed of light when the universe's large-scale structure was forming. This rules out certain dark matter candidates, like the ordinary neutrinos of the Standard Model, which are lightweight and therefore would have been moving relativistically in the early universe. Cold dark matter that was slow in the early universe, is what the cosmological data demands. The combination of terrestrial detector constraints and cosmological constraints has significantly narrowed the allowed parameter space for WIMP dark matter. And this narrowing, this progressive exclusion of possibilities, is in itself a scientific achievement. It means that wherever dark matter is hiding, we are getting increasingly precise about where it is not. And in a search space this large, if that kind of progress matters enormously. One of the most striking recent developments in dark matter searches comes from the intersection of gravitational wave astronomy and particle physics. When two neutron stars merge, the collision produces an enormous burst of energy across multiple channels: gravitational waves, gamma rays, optical light, radio waves. The properties of that burst are sensitive to the equation of state of nuclear matter at extreme densities, which in turn constrains the properties of the dark sector. If dark matter particles can accumulate inside neutron stars and affect their structure, the gravitational wave signal from neutron star mergers would encode that effect. This is a completely new way of searching for dark matter, using some of the most extreme objects in the universe as natural laboratories. It is in its infancy, but as gravitational wave detectors improve and the catalogue of observed mergers grows, it will become an increasingly powerful probe. The cosmic web itself is one of the most powerful tools for studying dark matter. Properties from a cosmological perspective. The detailed shape of the web, the thickness of the filaments, the sizes of the voids, the way galaxy clusters sit at the intersections of multiple filaments, all of these are sensitive to the nature of dark matter. Different dark matter models, WIMPs, axions, sterile neutrinos, ultralight dark matter, fuzzy dark matter, each produce subtly different predictions for the statistics of the cosmic web at small scales. And the increasingly detailed maps produced by surveys like those using the James Webb Space Telescope are beginning to have the sensitivity to distinguish between these predictions. What all of this searching, across so many different experimental approaches and so many different observational channels, adds up to is a picture of extraordinary scientific effort directed at a problem that refuses to yield easily. Dark matter is one of the most securely established phenomena in all of science, confirmed by completely independent lines of evidence using completely different physical principles. And it remains one of the deepest mysteries, because all of those lines of evidence tell us what dark matter does without telling us what it is. The universe has left us its gravitational footprints everywhere. And yet the creature that made them has not shown itself to any instrument we have built. This combination of certainty about the existence of something and complete ignorance about its nature is philosophically unusual and scientifically humbling. It is a reminder that our instruments, powerful as they are tools designed to see the kinds of things we already know how to look for. Dark matter, whatever it is, may require a new kind of instrument, a new physical principle, a new way of interacting with something that by its very nature has spent the entire history of the universe avoiding detection. Finding it may require not just more sensitive versions of existing detectors, but fundamentally new ideas about how to create a signal from something that barely interacts with anything. The Large Hadron Collider's role in this search is to try to produce dark matter directly, In the intense environment of high-energy collisions where enough energy is concentrated in a small enough volume that the heavy new particles required by many dark matter models can be created. The strategy works because of a principle called complementarity. If dark matter particles can scatter off ordinary matter in underground detectors, they can also be produced in particle colliders when ordinary matter is given enough energy to convert into mass. The two types of searches are sensitive to the same underlying physics, approached from different directions. When the LHC finds missing energy and momentum in its collision data, the amount of the mismatch and the energy distribution of the other particles produced in the collision can constrain the properties of whatever invisible particle carried away the missing momentum. So far, the LHC's searches for dark matter production in this mode have come up empty, in the same way as the underground direct detection experiments. The allowed parameter space has been constrained, but dark matter has not been found. And the mystery continues, patient and deep and dark, waiting for the instrument or the idea that will finally make it visible. Science proceeds in cycles of expectation and surprise, and the most interesting moments in any scientific enterprise are the ones where the surprise is genuine. Not just unexpected, but unexplainable within the current framework. The kind of surprise that does not fit into any of the existing categories, and therefore demands that the categories be rethought, carefully and patiently, until the new thing reveals what the old framework was missing. The Large Hadron Collider has been generating that kind of surprise with increasing frequency in recent years, and among the most intriguing of these discoveries are particles that the standard model, in its original form, simply did not predict. Not because the model got something wrong in the sense of making an incorrect prediction, rather because the model was silent about them, because they exist in a region of possibility that the original theory did not fully explore, because the space of what quark matter can do turns out to be richer than anyone had appreciated. The most notable of these are the exotic hadrons. Hadrons are particles made of quarks. In the original version of the standard model, hadrons come in two simple varieties: mesons, which contain one quark and one antiquark, and baryons, which contain three quarks. Protons and neutrons are baryons. This classification seemed complete and reasonable when it was first established, and for a long time, all observed hadrons fit neatly into one of these two categories. The world of hadrons appeared orderly and well understood. Then, beginning in the early 2000s and accelerating dramatically with the LHC, experimentalists began finding particles that did not fit. Particles with 4 quarks, 5 quarks, configurations that the simple meson-baryon classification had no room for. These are the tetraquarks and pentaquarks, and their existence is not forbidden by the deep principles of the strong force. The strong force, described by quantum chromodynamics, does allow more exotic combinations of quarks. It is just that those combinations are much harder to produce and much shorter lived, making them difficult to detect and easy to miss with instruments that are not sufficiently sensitive and fast. The LHC's ability to produce enormous numbers of collisions and record them with unprecedented precision has changed that completely. In the years of its operation, the machine has found dozens of exotic hadrons, particles with quark content and properties that go well beyond the simple proton-neutron picture. Each one is a small expansion of our understanding of what the strong force can produce. Each one is evidence that quark matter is richer and more varied than the original picture suggested. And each one raises questions about the details of how quarks bind together. Questions that quantum chromodynamics in principle contains the answers to, but that cannot currently be computed directly, because the strong force at these energy scales resists the mathematical techniques that work so well for other forces. Some of these exotic states have properties that are particularly puzzling. There are particles with masses and quantum numbers that do not match any simple quark model prediction. Particles that seem to sit at the exact threshold between two known states in ways that suggest they might be molecules of hadrons rather than simple multi-quark combinations. These threshold states, sometimes called hadronic molecules, would be loosely bound systems of two hadrons held together by residual strong force interactions, something like how protons and neutrons are held together into nuclei despite the neutrons having no electric charge. The idea of molecular states of hadrons opens a whole new vocabulary for describing what quark matter can be, a vocabulary that the simple meson-baryon classification never required. There are also particles that appear and disappear in ways that suggest complicated interference between different possible configurations. particles whose properties depend not just on what quarks they contain, but on the quantum mechanical superposition of different ways. Those quarks can be arranged, the same quark content but different internal geometries contributing to the same observable state. This is the full richness of quantum mechanics applied to a system as complex as a multi-quark state, and it makes the theoretical description of exotic hadrons genuinely challenging. Another category of unexpected results from the LHC involves what are called flavor anomalies. The Standard Model makes specific predictions about how different flavors of quarks and leptons should behave in particle decays, and how often one flavor should transform into another. For several years, experiments at the LHC found what appeared to be violations of these predictions. Specifically, certain decays of particles called B-mesons seem to produce muons at a different rate than electrons, when the Standard Model says those rates should be equal. This is a very specific kind of discrepancy. It would mean that the muon and the electron, which are supposed to be identical except for their mass, are being treated differently by some force or interaction that the Standard Model does not contain. The excitement around these flavor anomalies was considerable. Several theoretical frameworks beyond the Standard Model predicted exactly this kind of lepton universality violation, and theorists spent years developing models to explain it. The measurements seem to be pointing toward new physics in a very specific way, toward a new particle or force that preferentially coupled to muons rather than electrons, leaving its fingerprint in the ratio of decay rates. And then, in 2023, new and more careful analyses of the LHC data revised the significance of the anomalies significantly downward. The discrepancies, which had once seemed quite robust, were found to be smaller than initially reported, consistent with statistical fluctuations and subtle systematic effects in the analysis, rather than genuine physics signals. The excitement deflated. The anomalies did not disappear entirely, but they shrank to the point where they could no longer be presented as compelling evidence for new physics. This is science working correctly, even when it is disappointing. The initial measurements were reported, they were scrutinized, additional data was collected, the analysis was refined, the anomalies shrank. This process of challenge and revision is not a failure. It is the mechanism by which knowledge advances. False leads are eliminated, real signals survive. The patience required to sit with a potentially exciting result while it is being checked and rechecked is one of the least glamorous but most important qualities a scientist can have. And the willingness to report that a promising anomaly has shrunk, even after years of theoretical work building on the assumption that it was real, is one of the clearest signs that the scientific process is functioning as it should. The most intriguing results currently emerging from the LHC involve the precise measurement of quantities related to CP violation, the asymmetry between the behavior of matter and antimatter. The Standard Model predicts a specific amount of CP violation, arising from the mathematical structure of the weak force interactions. But the amount of CP violation in the Standard Model is not enough to explain why the universe contains matter at all. If matter and antimatter are destroyed whenever they meet, and if they were created in equal amounts in the Big Bang, they should have annihilated each other completely. The existence of matter requires additional CP violation beyond what the Standard Model provides. The LHC experiments are searching for those additional sources, measuring CP asymmetries in decays of various particles with ever-increasing precision, looking for deviations from Standard Model predictions that might point toward where the additional violation comes from. So far, the measurements are consistent with the Standard Model, but the precision continues to improve, and the sensitivity to new sources of CP violation increases with each new data set. The answer, if it is there, is getting harder and harder to hide. The story of how physics handles results that seem to point beyond the Standard Model, but then fail to hold up under scrutiny, is one of the most instructive in the history of science. It reveals the rigorous and self-correcting nature of the scientific process at its best, and it provides important context for interpreting the current landscape of hints and anomalies. In the years before the LHC began operation, there was considerable excitement about a set of measurements from a different accelerator, the Tevatron at Fermilab in the United States, that seemed to show evidence for a new particle. The signal appeared in a specific decay channel, with a statistical significance that was suggestive but not conclusive. Theorists produced papers proposing interpretations. The community discussed what the new particle might be, and then as more data accumulated and the analysis was refined, the signal faded. It did not meet the threshold for a discovery. It was a fluctuation, a statistical accident of the kind that inevitably occurs when you analyze enormous amounts of data looking for small signals. No new particle, the excitement dissipated, the papers were archived, science moved on. This kind of outcome is not a failure, it is the process working correctly. Physics requires that a claimed observation meet extremely high standards before it is accepted as genuine. The conventional threshold in particle physics is 5 sigma, meaning the probability of the result being a random fluctuation is less than 1 in 3.5 million. That threshold is set high because the stakes are high. A false discovery claim wastes enormous resources as other experiments scramble to confirm or extend it, and it damages the credibility of the field if it happens too often. The requirement of 5 sigma is not a bureaucratic formality. It is the hard-won lesson of decades of experience with the difficulty of extracting tiny signals from enormous backgrounds. The Muon G2 experiment provides perhaps the most sustained and carefully developed anomaly currently facing the standard model. The G2 of the Muon, technically called the Muon anomalous magnetic moment, is the tiny deviation of the Muon's magnetic moment from the value predicted by the simplest version of quantum electrodynamics. It arises from the muon's interactions with virtual particles, brief quantum fluctuations of fields, and because all particles and fields contribute, it is sensitive to any physics beyond the standard model. The calculation of the standard model prediction for G2 is one of the most precise computations in the history of physics, requiring contributions from quantum electrodynamics, the weak force, and the strong force, all calculated to remarkable precision. For many years, measurements of the Muon G2 showed a discrepancy with the standard model prediction at the level of 3 to 4 sigma, tantalizing, but not conclusive. In 2021, the Muon G2 experiment at Fermilab released its first result, and the discrepancy grew to more than 4 sigma. The excitement in the physics community was palpable. A 4 sigma discrepancy, while still below the conventional 5 sigma threshold for a discovery, is the kind of result that demands serious attention. If it held up and grew stronger with more data, it would be among the clearest signals of physics beyond the standard model ever observed. But then, in 2023, a new theoretical calculation of the standard model prediction for the Muon G2 appeared, performed using a different computational technique called lattice QCD. This calculation produced a value for the standard model prediction that was significantly different from the previous consensus, closer to the measured value, reducing the apparent discrepancy. The situation became complicated. 2 different theoretical calculations, using different methods, were producing different predictions for the same quantity. One was consistent with a significant discrepancy from experiment. The other suggested the discrepancy might be much smaller or might not exist. Resolving this theoretical disagreement requires more and better lattice QCD calculations, an ongoing computational effort involving some of the most powerful computers available for scientific research. Until the theoretical community reaches consensus on the correct standard model prediction, the significance of the experimental measurement remains ambiguous. The Muon G2 is simultaneously one of the most precisely measured and most theoretically uncertain quantities in particle physics, and the outcome of the ongoing theoretical work will determine whether it represents evidence for new physics or an artifact of a difficult calculation. This situation illustrates a broader challenge in the search for physics beyond the standard model. The discrepancies being searched for are small, because if they were large, they would have been found long ago. Detecting small discrepancies requires both extremely precise measurements and extremely precise theoretical predictions. And for quantities dominated by the strong force, like the contributions of hadronic vacuum polarization to the Muon G2, the theoretical predictions depend on computationally intensive lattice QCD calculations that are at the frontier of what current computers can handle. Improving these calculations is an active and difficult research program in its own right. The broader lesson is that the search for physics beyond the standard model is not just an experimental challenge, it is simultaneously a theoretical and computational challenge. The precision of the experiments has now reached the point where the limiting factor in many searches is not the experimental uncertainty, but the theoretical uncertainty. Building better theories, computing better predictions, is as important as building better detectors. There is a moment in any sufficiently deep investigation of the universe when you encounter a wall. Not the end of the territory, but a genuine wall, a place where two different descriptions of the world meet each other and cannot be reconciled, where the mathematics from one side looks completely different from the mathematics on the other, and every attempt to join them produces results that make no physical sense. Not results that are merely complicated or unexpected, but results that are mathematically undefined. Infinite quantities that signal a fundamental breakdown of the framework rather than a difficult but solvable calculation. Physics has been standing in front of that wall for about a century. On one side of the wall is general relativity, Einstein's theory of gravity, the framework that describes how mass and energy curve space-time, and how that curvature tells matter how to move. It is a theory of smooth, continuous fields, of gradual variations, of the large-scale geometry of space and time. It has been tested to extraordinary precision across an enormous range of phenomena. It predicted the bending of light by the sun, confirmed during a solar eclipse in 1919. It predicted the existence of gravitational waves, thus confirmed by LIGO in 2015 when two merging black holes a billion light-years away sent ripples through space-time that were detected as a tiny vibration in the distance between two mirrors separated by 4 kilometers. It predicted the behavior of black holes in detail that has been confirmed by the first direct imaging of the black hole at the center of the Milky Way. It is one of the most successful and precisely verified theories in all of science. On the other side of the wall is quantum mechanics, the framework that describes how matter and energy behave at the smallest scales. It is a theory of discrete quantities, of probability amplitudes, of the inherent uncertainty that pervades the behavior of elementary particles. It has also been tested to extraordinary precision. It underlies all of chemistry, all of material science, all of modern electronics. The computer or phone or tablet you might be reading this on exists because of quantum mechanics. Every transistor, every logic gate, every display pixel depends on quantum mechanical effects that engineers have learned to exploit with extraordinary precision. Both theories are extraordinarily successful in their own domains. Both have been confirmed by experiments to multiple decimal places, and they absolutely cannot be combined into a single consistent framework without producing mathematical absurdities. This is not a minor technical issue that clever mathematicians have simply not yet resolved. It is a deep conceptual problem. The two pillars of modern physics are mutually inconsistent at a fundamental level. The reason for this incompatibility runs deep. General relativity is a classical theory in the technical sense. It describes the gravitational field as a smooth, continuous geometric entity, the curvature of space-time. Quantum mechanics, on the other hand, insists that everything should be quantized, that fields should have discrete excitations, that there should be a particle associated with the gravitational field, just as there are particles associated with the electromagnetic and weak and strong fields. Theorists call this hypothetical gravitational particle the graviton, and when you try to construct the quantum field theory of the graviton, the mathematics breaks down irreparably. The specific problem is renormalization. In quantum field theory, calculations of physical quantities like particle masses and interaction probabilities produce intermediate results that are infinite. The process called renormalization removes these infinities by recognizing that the physical measured quantities, like the electron mass, absorb the infinities, and the calculated quantities, expressed in terms of measured inputs, are finite and well-defined. This procedure works for the electromagnetic, weak, and strong forces. It does not work for gravity. The infinities that arise in quantum gravitational calculations cannot be absorbed into a finite number of measured parameters. They proliferate endlessly, requiring an infinite number of parameters to be fixed by experiment, which means the theory has no predictive power. This is the wall, and the most developed attempt to get around it, rather than through it, is string theory. String theory proposes that the fundamental objects of physics are not point particles, but tiny one-dimensional vibrating strings of energy. Different modes of vibration of these strings correspond to different particles, and the beautiful and crucial thing is that among the possible vibration modes of a closed string, there is always one that corresponds to a massless spin-2 particle, which is precisely the graviton. Gravity emerges automatically from the mathematics of strings. You do not have to add it separately. And unlike the quantum field theory of point particles, string theory does not produce the unrenormalizable infinities that make point-particle quantum gravity nonsensical. String theory also requires the existence of extra dimensions of space. The mathematics of vibrating strings is only consistent in 10 or 11 dimensions of space-time, depending on the specific version of the theory. The extra dimensions must be compactified, curled up at scales so small that they would be invisible to any current experiment. And the way they are compactified, the specific shape of the tiny extra-dimensional space, determines the particle content and forces of the observable universe. The Large Hadron Collider was built in part to look for evidence of extra dimensions. If the extra dimensions exist at scales not too far below what the LHC can probe, there would be signatures. The production of Kaluza-Klein particles, the higher dimensional analogues of ordinary particles, deviations from the expected strength of gravity at short distances. In some models, even the production of microscopic black holes, tiny gravitationally collapsed objects that would evaporate almost instantaneously through Hawking radiation, leaving characteristic sprays of particles. None of these signatures have been found. The constraints on extra dimensions have been pushed to smaller and smaller scales. But the absence of a detection is not the same as a disproof. String theory is flexible enough that the signatures might be present at energies the LHC cannot reach. What gravity's refusal to fit into the quantum framework tells us is that the story of physics is not finished. The two most successful theories in the history of science are mutually inconsistent at their foundations, and somewhere in the resolution of that inconsistency, in the theory of quantum gravity that physics has not yet found, are likely the answers to some of the other open questions: the nature of dark matter, the origin of the matter-antimatter asymmetry, the mechanism behind cosmic inflation, the true nature of the vacuum. These are not unrelated problems. They are facets of the same deep question about the structure of reality at its most fundamental level. The philosophical implications of the incompatibility between quantum mechanics and general relativity go deeper than merely saying that two theories do not fit together and that we need a better one. They touch on fundamental questions about what space and time actually are, about whether space-time is smooth and continuous all the way down to arbitrarily small scales, or whether it has a fundamental graininess at some level, just about whether the universe is fundamentally quantum mechanical in a way that implies space-time itself must be described by a quantum state. In general relativity, space-time is the fundamental entity. Matter and energy curve it. Its curvature tells matter how to move. Space-time is not a fixed background against which physics happens. It is a dynamical entity that participates in the physics. This was Einstein's great insight, and it is why the prediction of gravitational waves, ripples propagating through the fabric of space-time itself, was such a profound confirmation of the theory. The detection of gravitational waves by LIGO in 2015 was not just a confirmation of a prediction. It was the first direct observation of space-time itself behaving dynamically, stretching and compressing as the waves pass through. But in quantum mechanics, there is always a background. Quantum fields are defined on a space-time background. The states of the fields evolve on that background. There is no quantum mechanical formulation of what it means for the background space-time itself to be in a quantum superposition. No natural way to extend the quantum mechanical framework to include the dynamical space-time of general relativity. The quantum of the gravitational field, the graviton, would be a particle propagating on space-time, the same space-time that it is supposed to be describing. The self-referential nature of this creates mathematical problems that go beyond anything encountered in the quantum field theories of the other forces. Loop quantum gravity is one approach to resolving this impasse that takes a different direction from string theory. Rather than starting with extra dimensions and strings, loop quantum gravity takes the lessons of general relativity seriously and tries to construct a quantum theory of spacetime itself. In this approach, spacetime is not a smooth continuous manifold at all scales but has a discrete structure at the Planck scale. Space is made of finite quanta. The area of a surface has a minimum possible value. The volume of a region has a minimum possible value. Below the Planck scale, the concepts of area and volume and distance lose their meaning. This discreteness of spacetime has potentially observable consequences. If spacetime is discrete at the Planck scale, then light propagating over cosmic distances might experience a tiny energy-dependent delay, higher energy photons arriving slightly later than lower energy ones from the same source. This effect would be so small that it would be undetectable in almost any practical situation. but for photons travelling over the enormous distances separating gamma-ray bursts from Earth, the cumulative effect might be large enough to measure. Observations of gamma-ray bursts by the Fermi Gamma-ray Space Telescope have placed constraints on this effect that are already probing Planck-scale physics. So far, no energy-dependent delay has been detected, which rules out some of the simplest versions of spacetime discreteness, but the constraints continue to improve. Another window into quantum gravity physics comes from the study of black holes, which are perhaps the most extreme environments in the universe and the places where quantum gravitational effects are expected to become important. A black hole is a region of spacetime where the gravitational field is so strong that nothing, not even light, can escape. The boundary of this region is called the event horizon, and it is one of the most fascinating objects in theoretical physics. Stephen Hawking showed in 1974, using a semi-classical calculation that combines elements of quantum mechanics and general relativity without fully unifying them, that black holes are not perfectly black. They emit radiation, now called Hawking radiation, with a temperature proportional to the inverse of their mass. This radiation means that black holes slowly evaporate, losing mass and eventually disappearing entirely. The Hawking radiation calculation is one of the most important results in theoretical physics because it sits at the precise interface between quantum mechanics and general relativity, using both in a way that reveals a deep tension. The tension is called the black hole information paradox. According to quantum mechanics, information can never be truly destroyed. The process of quantum evolution is reversible in principle. If you know the complete quantum state of a system at one time, you can in principle recover the state at any earlier time. But when a black hole forms and then evaporates through Hawking radiation, the quantum information about the matter that fell into the black hole seems to be destroyed. The Hawking radiation is thermal, random, carrying no information about what fell in. The black hole disappears, and with it all information about its contents. This is a paradox because quantum mechanics says information must be conserved, and general relativity says it is not. Something is wrong. Either quantum mechanics breaks down near the event horizon of a black hole, or general relativity does, or both are descriptions of some deeper framework that behaves differently than either. The resolution of the black hole information paradox is one of the most actively debated problems in theoretical physics, and it has led to a remarkable convergence of ideas connecting quantum information theory, holography, and the structure of spacetime. The holographic principle, proposed by Gerard de Hooft and Leonard Susskind in the 1990s, suggests that the information content of a volume of space can be encoded on its bounding surface, that the physics inside a region is somehow determined by, or equivalent to, physics on the surface surrounding it. This is deeply counterintuitive. We expect the amount of information in a volume to scale with the volume, not with the surface area, but black hole thermodynamics, specifically the Bekenstein-Hawking entropy formula, that relates the entropy of a black hole to its surface area rather than its volume, suggests that the holographic principle is real. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, provides a precise realization of holography in a specific mathematical setting. It demonstrates that a theory of quantum gravity in a particular kind of curved spacetime is mathematically equivalent to a quantum field theory without gravity living on the boundary of that spacetime. This is a profound and unexpected result. It says that the same physics can be described in two completely different ways, one involving gravity and one not, with the two descriptions being related by a specific mathematical dictionary. Quantities calculated in one description have precise counterparts in the other. The ADS-CFT correspondence is one of the most influential ideas in theoretical physics of the past 30 years. It has provided new tools for calculating properties of strongly coupled quantum field theories, including properties of the quark-gluon plasma created in heavy ion collisions at the LHC. It has given new perspectives on quantum information and entanglement in gravitational systems. And it has provided the most concrete realization yet of the idea that gravity and quantum mechanics are not simply incompatible, but related in a deeper way that a full quantum theory of gravity must somehow capture. All of this, the loop quantum gravity approach, the holographic principle, the ADS-CFT correspondence, the information paradox, the Hawking calculation, they are pieces of a puzzle whose full picture has not yet come into focus. But the outline of the picture is becoming clearer. It suggests that spacetime is not fundamental. It suggests that spacetime emerges from something more basic, some deeper structure that is intrinsically quantum mechanical, and that the geometry we experience as space and time is a kind of effective description that is accurate in the regimes we have access to, but that breaks down when pushed to extremes. Finding out what that deeper structure is, and connecting it to the measurements being made at the Large Hadron Collider and in cosmological observations, is the great challenge of 21st century physics. Hold your left hand up in front of a mirror. The reflection looks like a right hand. The mirror has reversed something fundamental, not just the image, but the handedness of what it reflects. In physics, this kind of reversal has a technical name. It is called parity, and for a long time, physicists assumed that the laws of physics were symmetric under parity. That if you built a mirror universe where left and right were switched and the directions of all spatial coordinates were reversed, the same physical processes would occur in the same ways. The laws of nature, it seemed reasonable to assume, should not care about the difference between left and right. They should be the same in a mirror as in the original. Then, in 1956, a pair of theorists named Tsung-Dao Lee and Chen-Ning Yang proposed, based on a careful examination of the available evidence, that the weak force might not respect this symmetry. They pointed out that parity conservation in the weak force had never actually been rigorously tested, that it had been assumed rather than measured. They proposed an experiment that could test it. Chien-Shiung Wu, an experimental physicist at Columbia University, carried out the experiment using cobalt-60 atoms in a magnetic field, measuring whether radioactive decay by the weak force had a preferred direction. It did, enormously and unambiguously. The weak force is not mirror symmetric. It has a preference for left-handed particles over right-handed ones. The universe, at the level of the weak force, knows the difference between left and right. Li and Yang received the Nobel Prize the following year. Wu, who actually performed the decisive experiment, did not, an omission that has been noted with some frequency in discussions of recognition in science. But the physics result was unambiguous and world-changing. Parity is not a symmetry of nature. The laws of physics are not the same in a mirror universe. The universe has a handedness. Parity violation was just the beginning. Once physicists accepted that the weak force was not symmetric under spatial inversion, they wondered whether it might still be symmetric under the combination of parity inversion and charge conjugation, the mathematical operation that switches particles and antiparticles. If you take the mirror image and also replace every particle with its antiparticle, would you get a universe whose physics is identical to ours? This combined symmetry is called CP symmetry, and it seemed like a natural candidate for a fundamental conservation law. In 1964, James Cronin and Val Fitch discovered that CP symmetry is violated in the decays of certain particles called kaons. The violation was small but definitive. This was, in many ways, an even more profound discovery than the original parity violation. CP violation means that the laws of physics genuinely distinguish between matter and antimatter. The universe treats them differently. And this asymmetric treatment has a consequence of the most fundamental importance. It means that the laws of physics could, in principle, have been responsible for generating more matter than antimatter in the early universe, creating the matter-dominated cosmos we inhabit today. But here is the problem. The amount of CP violation in the Standard Model, arising from the complex phase in the quark mixing matrix, is real and measured and well confirmed. But it is insufficient to explain the observed matter-antimatter asymmetry of the universe by many orders of magnitude. The Standard Model's CP violation can account for some asymmetry, but not nearly enough. The matter in the universe, every atom in every star in every galaxy, required more CP violation in the early universe than the Standard Model can produce. This means additional sources of CP violation must exist, and finding them, measuring them, understanding where they come from and how large they are, is one of the central missions of the LHC and related experiments. The LHCb detector at the Large Hadron Collider is specifically optimized for this search, designed to measure the properties of particles containing bottom quarks with extraordinary precision, because those particles are particularly sensitive probes of CP violation. Every analysis it performs is a check on whether the Standard Model's account of CP violation is complete, or whether there are additional terms missing from the equations. The neutrino sector offers another possible source of CP violation that could be even more significant. Neutrinos, the ghostly particles that pass through ordinary matter, almost without interaction, were originally assumed to be massless in the Standard Model. Then experiments showed that they have mass, that the three types of neutrinos transform into each other as they travel through space or through matter, and there is no principle that would prevent the neutrino sector from having its own form of CP violation, distinct from the quark sector violation that Cronin and Fitch discovered. If CP violation in the neutrino sector is large, it could potentially be the dominant source of the matter-antimatter asymmetry that allowed the universe to exist. Measuring CP violation in neutrinos requires enormous experiments. Neutrinos interact so rarely with ordinary matter that detecting them requires massive volumes of material instrumented with sensitive detectors. And measuring the CP asymmetry requires sending beams of neutrinos and separately beams of antineutrinos over hundreds of kilometers to a far detector, and comparing the oscillation patterns. If the pattern for neutrinos differs from the pattern for antineutrinos, CP is violated in the neutrino sector. Experiments designed to make this measurement are among the most ambitious scientific projects currently underway. They represent the combined effort of thousands of physicists, engineers, and technicians across dozens of countries, building instruments at the frontier of sensitivity for what may be the most fundamental question in science. Why does matter exist? The answer may be encoded in the behavior of neutrinos traveling through the Earth in the darkness, and the measurements needed to read that encoding are exquisitely difficult and extraordinarily important. The search for CP violation beyond the Standard Model connects in subtle but important ways to the large-scale structure of the universe that astronomers and cosmologists study. The matter-antimatter asymmetry of the universe is not just a quirky fact about the relative abundance of protons and electrons compared to antiprotons and positrons. It is the foundation of everything that exists. Without it, without the process in the early universe that created slightly more matter than antimatter and allowed the excess to survive when the bulk annihilated, there would be no atoms, no molecules, no chemistry, no stars, no planets, no life. The universe would be a sea of photons and neutrinos, expanding into an eternal, featureless equilibrium. The conditions required for the generation of a matter-antimatter asymmetry, from initially symmetric initial conditions, were spelled out by Andrei Sakharov in 1967. He identified three requirements, now called the Sakharov conditions. First, there must be processes that violate baryon number, that create baryons without creating the corresponding antibaryons. Second, there must be CP violation, so that matter and antimatter are treated differently in these baryon number violating processes. Third, these processes must occur when the universe is out of thermal equilibrium, because in thermal equilibrium, the reverse of any matter-producing process would be equally likely, washing out any asymmetry that built up. The Standard Model satisfies all three of these conditions in principle. Baryon number violation occurs in the Standard Model through a process called Sphaleron transitions, which become active at high temperatures. CP violation is present through the complex phase in the quark mixing matrix. And the electroweak phase transition, the event in the early universe when the Higgs field settled into its current vacuum configuration and gave particles their masses, could in principle have been a strongly first-order phase transition, proceeding in a way that was far from thermal equilibrium. The problem is that each of these Standard Model mechanisms is insufficient by a large margin. The Sphaleron transitions are efficient, but the CP violation from the quark mixing matrix is too small by many orders of magnitude to generate the observed asymmetry. And the electroweak phase transition, rather than being strongly first order as required, is in the Standard Model a smooth crossover, much too gradual to provide the necessary out-of-equilibrium conditions. The Standard Model satisfies the Sakharov conditions qualitatively, but fails them quantitatively. This means that bariogenesis, the process that generated the matter-antimatter asymmetry, required physics beyond the Standard Model. And unlike many of the other open problems in particle physics, bariogenesis cannot have happened any time other than the very early universe. The process had to occur when the universe was hot enough for Sphaleron transitions to be active, and the Higgs field was settling into its vacuum. That places bariogenesis at temperatures well above those accessible to any collider. We cannot directly recreate the conditions of bariogenesis in a laboratory. We can only look for the traces it left behind. Those traces are everywhere, in the sense that every atom in the universe is a trace of bariogenesis, but the specific traces that constrain models of bariogenesis, that distinguish between different mechanisms, are the CP violation measurements and the baryon number violating process rates that experiments like the LHC can access. If a particular model of bariogenesis predicts a specific pattern of CP violations in B-meson decays, or a specific modification of the electroweak phase transition in the presence of new particles, the LHC measurements can test those predictions and either support or rule out the model. The connection between the LHC and the origin of everything that exists is not metaphorical. The machine is not just probing abstract questions about particle physics, it is probing the conditions that made the universe habitable, that allowed matter to exist, that allowed structure to form and complexity to emerge and life to appear. Every measurement of CP violation, every search for new sources of baryon number violation, every test of the electroweak phase transition is a step toward understanding why there is something rather than nothing. The neutrino connection to bariogenesis deserves particular attention, because the leading theoretical framework for generating the observed baryon asymmetry, called leptogenesis, works through neutrinos rather than quarks. In leptogenesis, heavy right-handed neutrinos, particles that do not appear in the standard model but are natural extensions of it, CERN, are created in the early universe and then decay with CP violation, creating more leptons than antileptons. Sphaleron transitions then convert this lepton asymmetry into a baryon asymmetry, the baryon asymmetry we observe today. Leptogenesis requires heavy right-handed neutrinos that are far too heavy to be directly produced at the LHC, but it also requires CP violation in the neutrino sector that can in principle be measured in neutrino oscillation experiments. If the CP violating phase in the neutrino mixing matrix is large, that supports leptogenesis as a mechanism. If it is small or zero, leptogenesis in its simplest forms becomes harder to accommodate. The measurement of this phase, in experiments that send neutrino beams through the Earth over hundreds of kilometers, is therefore directly relevant to understanding the origin of all matter in the universe. The universe is not a collection of isolated phenomena. Every particle physics experiment, every cosmological observation, every theoretical framework is a thread in a single tapestry. The LHC measurements of CP violation in B-meson decays are connected to the neutrino oscillation experiments searching for CP violation in the lepton sector, which are connected to the cosmological observation of the baryon asymmetry, which is connected to the theoretical framework of leptogenesis, which requires heavy right-handed neutrinos whose properties are constrained by the LHC searches for new particles at high energies. Pull on any thread and the others move. There is something almost meditative about the idea that most of the universe is made of things we cannot see and do not understand. It is not a comfortable thought exactly, but it is a clarifying one. It reminds you that the bright, visible, tangible world is a thin layer of something much larger, the way the surface of the ocean is a thin layer of something that extends miles beneath, vast and dark and full of structures that the sunlight never reaches, full of currents and pressures and life forms that have never been seen from above. The invisible web of the universe is the cosmic web, the network of dark matter filaments and voids and nodes that shapes the distribution of visible matter on the larger scales. When the universe was very young, it was an almost perfectly uniform soup of hot plasma. The temperature was so high that particles could not form stable structures. Protons and neutrons and electrons existed, but they were swept along in the plasma, unable to combine into atoms, unable to clump into anything more complex. The universe was bright and hot and nearly featureless. Nearly because quantum mechanics ensures that the initial conditions of the universe were not perfectly uniform. There were tiny fluctuations, minute variations in density from one region to another, created by quantum uncertainty in the earliest fractions of a second after the Big Bang. These fluctuations were not classical ripples, they were quantum noise, promoted to cosmic scales by the rapid expansion of the early universe. These tiny fluctuations are the seeds of everything, every galaxy, every star, every planet. Every person is the consequence of a quantum fluctuation that happened in the first fraction of a second after the universe began. Gravity spent the next 13 billion years amplifying those fluctuations. The slightly denser regions attracted more material. The slightly less dense regions lost material to their neighbours. Over hundreds of millions of years, this process of gravitational collapse built the first stars, the first galaxies, and eventually the enormous structures, clusters of galaxies, walls, filaments and voids that we observe today. Dark matter was crucial to this process. Because dark matter interacts only through gravity, it began forming structures before ordinary matter could. The ordinary matter, the protons and electrons and atoms, and was still coupled to radiation during the first 400,000 years of the universe, carried along by the pressure of photons, unable to clump freely. But dark matter could begin collapsing immediately, forming potential wells into which ordinary matter later fell when the universe cooled enough for atoms to form and the radiation pressure dropped. The dark matter structure came first. The visible matter followed, streaming along the invisible channels that dark matter had already carved. The galaxies and clusters we see today are embedded in dark matter halos, invisible gravitational structures that contain most of the mass and that formed before the stars ever ignited. The cosmic web of dark matter filaments is the skeleton. The visible universe of stars and galaxies is the flesh. This is not a metaphor. It is a description of the actual architecture of the universe, confirmed by simulations that begin with the observed properties of the early universe and evolve forward in time using the known laws of physics, producing a large-scale structure that matches the observed distribution of galaxies with striking accuracy. The new maps of dark matter structure produced by the James Webb Space Telescope and other modern instruments have made this skeleton visible in extraordinary detail. By measuring the tiny distortions in the shapes of background galaxies caused by the gravitational lensing effect of intervening dark matter, astronomers can reconstruct where the dark matter is concentrated, mapping the invisible web directly. What these maps show is a universe that is not uniformly filled with matter. It is organized, say deeply and intricately organized, into a network of filaments and nodes and voids that extends across billions of light years. The structure is hierarchical, small clumps embedded within larger ones within still larger ones, in a self-similar pattern that emerges naturally from the gravitational amplification of the initial quantum fluctuations. The dark matter maps built from this data reveal something that has been theorized for decades but never seen at this resolution: a network, an architecture, the invisible skeleton on which every visible thing in the universe is arranged. Dense nodes where galaxy clusters sit, their massive dark matter halos dominating the local gravitational landscape. Connecting those nodes, elongated filaments of moderate density stretching tens of millions of light years, carrying streams of galaxies between clusters, flowing along invisible channels carved by the underlying dark matter structure. Surrounding the filaments, enormous voids, regions so depleted of matter that galaxies are almost entirely absent from them, vast empty caverns in the fabric of the cosmos. What strikes a careful observer about all of this is the deep connection between the cosmic web and the physics being explored at the Large Hadron Collider. The dark matter that forms the backbone of the web is made of particles. Those particles have properties, masses and interaction cross-sections and decay rates that determine how the web formed and how it continues to evolve. Understanding what those particles are is essential for understanding the full history of the universe. The dark matter maps from astronomical observations constrain the properties of dark matter particles from the cosmological side. The LHC searches constrain them from the particle physics side. The two approaches together paint a picture that neither could achieve alone. There is another connection between the LHC and the cosmic web that goes even deeper. The initial quantum fluctuations that seeded the large-scale structure of the universe originated in a period called cosmic inflation. Inflation is the theory that the universe underwent an extraordinarily rapid period of exponential expansion in the first tiny fraction of a second after the Big Bang, stretching quantum fluctuations from microscopic to cosmic scales in an instant. Different models of inflation make different predictions about the properties of the fluctuations, and upcoming cosmological observations are pushing into the regime where these distinctions become measurable. The particle physics perspective from the LHC helps narrow down which inflation models are physically reasonable, creating a connection between the underground machine in Switzerland and the large-scale structure of the entire observable universe. The study of the cosmic web connects in surprising and beautiful ways to some of the most fundamental questions in particle physics. The web is not just a large-scale structure that astronomers observe, it is a record, encoded in the distribution of galaxies across billions of light years of the physics of the very early universe. The particular statistics of the web, how structures cluster on different scales, how many voids there are and how large they are, how the filaments are distributed, all of these are sensitive to the properties of the particles and fields that shape the early universe. Neutrinos provide one of the most striking examples of this connection. Neutrinos have mass, as established by the observation of neutrino oscillations, but their masses are extraordinarily small, far smaller than any other known particle. The sum of all three neutrino masses is constrained to be less than a fraction of an electron volt, making them the lightest known massive particles by an enormous margin. Despite this tiny mass, neutrinos were abundantly produced in the early universe, and because they move at nearly the speed of light, they stream freely through the universe on large scales, preventing the formation of structure on scales smaller than a certain characteristic length that depends on their mass. This neutrino free streaming leaves a detectable imprint on the large-scale structure of the universe. By precisely mapping the distribution of galaxies on large scales, cosmological surveys can measure the small but non-zero suppression of structure caused by neutrino free streaming, and from that suppression, they can constrain the sum of neutrino masses. This is an extraordinary example of using the largest scales in the universe, the distribution of galaxies across billions of light years, to measure one of the most fundamental properties of the smallest known massive particles. The cosmic web is a neutrino detector of cosmic scale. Current constraints from cosmological observations put the sum of neutrino masses at less than about 1/10 of an electron volt, a constraint that is already more stringent than what direct laboratory measurements of neutrino mass can achieve. Future surveys, mapping the three-dimensional positions of tens of millions of galaxies with unprecedented precision, are expected to either measure the sum of neutrino masses directly or push the upper limit down to levels where individual neutrino masses can begin to be distinguished. This connection between galaxy surveys and fundamental particle physics is one of the most productive in modern science. The cosmic web also encodes information about the epoch of reionization, the period around 1 billion years after the Big Bang when the first stars and galaxies formed and their ultraviolet light reionized the neutral hydrogen that had filled the universe after recombination. The way this reionization proceeded, how quickly it happened and whether it was driven primarily by galaxies or by quasars, or some combination, left imprints on the large-scale structure that can be extracted from observations. The James Webb Space Telescope's observations of the earliest galaxies, including those found in the first few hundred million years after the Big Bang, are directly informing models of reionization by showing how many such galaxies existed and how bright they were. But perhaps the deepest connection between the cosmic web and fundamental physics comes from the study of primordial non-Gaussianity. The fluctuations that seeded the cosmic web were, in the simplest models of inflation, purely Gaussian, meaning their statistical properties were completely determined by their power spectrum. But more complex inflationary models with multiple fields or unusual dynamics, predict small but detectable non-Gaussian signatures, correlations between fluctuations that go beyond what a simple Gaussian distribution would produce. Detecting these non-Gaussianities in the distribution of galaxies would provide direct information about the physics of inflation, about the nature of the fields that drove the exponential expansion of the early universe. The planned surveys of the next decade, including Euclid, the Nancy Grace Roman Space Telescope, and the Dark Energy Spectroscopic Instrument, are designed with the sensitivity to either detect primordial non-Gaussianity or place very tight limits on it. A detection would be a revolutionary discovery, providing our first direct information about the physical mechanism behind inflation. A non-detection would rule out large classes of inflationary models and constrain the simplicity of the initial conditions. Either way, the measurement will significantly sharpen our understanding of the very beginning. The Large Hadron Collider's connection to all of this comes through the particle physics models that inflation requires. Inflation needs a scalar field, the inflaton, that drove the exponential expansion and then reheated the universe by decaying into ordinary particles when inflation ended. The properties of the inflaton, its mass, its self-coupling, its couplings to other fields, determine the details of the inflationary dynamics and the properties of the fluctuations it produced. Different inflationary models correspond to different particle physics models, and some of those models have testable implications at collider energies. In particular, certain models of inflation predict the existence of additional scalar particles with masses in the range accessible to the LHC. If such particles exist, they would show up in the LHC data as new resonances, bumps in the invariant mass distributions of specific final states. No such bumps have been found yet, but the search for new scalar particles beyond the Higgs boson is one of the ongoing programs at the LHC, and a discovery in this channel would connect directly to cosmology in a very concrete way, potentially identifying the inflaton or a particle connected to it. The cosmic web is, in this sense, a giant billboard advertising the physics of the early universe, and the LHC is one of the tools for reading what it says. The two approaches, astronomical surveys mapping the large-scale structure and accelerator experiments probing the small-scale structure, are asking the same questions from opposite directions, and the answers they give, when put together carefully, paint a picture that neither could achieve alone. There is a boundary around us that we can never cross. Not a wall exactly, more like a horizon, the kind you see when you stand on a beach and look out to sea. The ocean continues beyond it. You simply cannot see that far from where you stand. Although the boundary of the observable universe is defined not by the edge of space, but by the edge of time, the distance from which light has had just enough time to travel to reach us in the 13.5 billion years since the Big Bang. Everything within that distance we can, in principle, see. Everything beyond it is forever hidden, its light still travelling toward us, not yet arrived, perhaps never to arrive if the expansion of space is carrying those regions away from us faster than the light from them can approach. But the observable universe is not the deepest limitation on what we can know. There is another horizon, closer and more fundamental, the horizon of the Planck scale. Below certain scales of distance and energy, the concepts of classical space-time break down entirely. At the Planck length, a scale vastly smaller than any particle we have ever directly observed, the quantum fluctuations of space-time itself become so large that space and time cease to be well defined. The smooth fabric of general relativity dissolves into something that physicists sometimes call quantum foam, a churning uncertain geometry where the very concepts of position and distance become meaningless, where the distinctions between space and time and matter and energy blur into something that our current mathematics can barely gesture toward. The Large Hadron Collider probes the universe at scales that are small by everyday standards, but still enormously large compared to the Planck scale. Between the scales the LHC can access and the Planck scale, there is a vast desert of physics that no current or near-future instrument can directly explore. And yet that desert is not empty. Somewhere in it, at some energy between what the LHC can reach and the Planck scale, the forces of the Standard Model are thought to unify. The coupling constants of the strong, weak and electromagnetic forces run with energy in a specific way, and the calculations suggest that they might converge to a single value at very high energies, pointing toward a grand unified theory in which all three are different aspects of a single, deeper force. Grand unified theories predict the unification of forces at energies around 10 to the power of 15 times the mass of the proton, far above what any conceivable accelerator can reach directly. But they also predict observable consequences at accessible energies. The most dramatic of these is proton decay. In the Standard Model, protons are stable particles. The conservation of baryon number prevents them from decaying, but in grand unified theories, baryon number is not absolutely conserved. The processes that unify quarks and leptons at very high energies allow, at low energies, a tiny but non-zero probability for a proton to decay into a positron and a neutral pion, or similar final states. Experiments to detect proton decay are among the most patient in all of science. They consist of enormous underground volumes of water or other material, instrumented with sensitive light detectors, watching for the tiny flash of light that would signal a proton's decay. The searches have been going on for decades. No proton has yet been seen to decay. The experimental limits on the proton lifetime have been pushed to around 10 to the power of 34 years, meaning that if you watched a proton for that long, you would have a roughly even chance of seeing it decay. Since the universe is only about 10 to the power of 10 years old, the patience required to directly observe a proton decay in real time is literally cosmic. But with enough protons watched simultaneously, the statistics become practical, and the experiments are genuinely looking. The LHC cannot directly probe unification scale energies, but it can look for the low-energy manifestations of grand unified physics in the specific patterns of particle masses and mixing angles, in the rates of certain rare processes, in the precise values of coupling constants at the energies it can probe. By measuring these quantities with high precision, physicists can test whether the low-energy data is consistent with high-energy unification. And if so, what kind of unification is preferred? Quantum entanglement enters this story in a way that has become increasingly important in recent years. The LHC has confirmed quantum entanglement in top quarks, the heaviest known fundamental particle, created in pairs in high-energy collisions. The two top quarks in a pair are produced in an entangled quantum state, meaning that their quantum numbers are correlated in a way that cannot be explained by any local classical mechanism. Measuring the properties of one member of the pair instantaneously constrains what you can find when you measure the other, even after they have separated. This is one of the most fundamental and strange features of quantum mechanics, and seeing it manifest in heavy quarks at the energy frontier is a reminder that quantum weirdness is not just a property of simple systems, it pervades the universe at every scale. The edge of observation is not just a limit on what we can see, it is a constraint on what we can understand directly. But physics has developed powerful indirect methods for peering beyond the directly observable, theoretical frameworks constrained by low-energy data. Cosmological observations that encode information about the early universe, gravitational wave astronomy that opens new windows on extreme environments. The Large Hadron Collider is one of the tools for reading these indirect signals, for tracing the fingerprints that high-energy physics leaves in the accessible world, for finding in the careful measurement of the ordinary the hints of something extraordinary that lies just beyond the edge of what we can currently reach. The question of what lies beyond the observable universe is one of the deepest in cosmology, and it connects in unexpected ways to the physics being explored at the LHC. The observable universe is the sphere from which light has had time to reach us since the Big Bang, but the universe almost certainly extends beyond that sphere, and the physics of inflation suggests it extends vastly beyond it, possibly infinitely beyond it. In inflationary models, the universe before inflation was small enough that quantum fluctuations could create correlations across the entire pre-inflationary volume. Inflation then expanded that volume by an extraordinary factor, stretching those correlations to scales far larger than the observable universe. The result is a universe that is globally far more uniform than it would be without inflation, because the regions we can observe today were all in causal contact before inflation and had time to come to thermal equilibrium. But the regions beyond our horizon, carried away from us by the inflationary expansion, are also part of the same universe, governed by the same physical laws that emerged when inflation ended and reheating occurred. In the eternal inflation framework, however, different regions of the universe may not share the same physical laws. In eternal inflation, the inflationary expansion never completely stops everywhere. Different regions of space undergo the end of inflation at different times, and each region settles into a different vacuum from the string landscape. Our observable universe is one bubble in an enormous collection of bubbles, each with its own physical constants, its own particle masses, its own effective laws of physics, the multiverse of eternal inflation. This framework has profound and deeply uncomfortable implications for how we interpret the physical constants we observe. If the laws of physics in our observable universe were selected, in some sense, by the requirement that they allow structures like atoms and stars and galaxies and observers to form, then asking why our physical constants have the values they do is not a question with a fundamental answer. In terms of underlying dynamics, the answer is environmental. We live in the bubble we live in because it is one of the bubbles where the constants allow our existence. In other bubbles, the constants are different, and observers like us, if they exist, ask the same question and get a similar environmental answer. This is deeply unsatisfying to many physicists. It seems to remove the explanatory ambition from physics to replace the goal of understanding why the constants are what they are, with the observation that they had to be something compatible with our existence. Steven Weinberg used anthropic reasoning in 1987 to predict the value of the cosmological constant, arguing that it must be small enough to allow galaxies to form but not so small as to seem contrived. The subsequent discovery that the cosmological constant is indeed small but non-zero, exactly in the range Weinberg had identified as anthropically plausible, is taken by some as evidence for the multiverse, and by others as a coincidence. The Large Hadron Collider cannot directly probe the multiverse, No instrument can, by definition, because other bubbles in the multiverse are outside our observable horizon. But the LHC can test theories that motivated the multiverse picture, primarily the string theory landscape, by searching for the specific particle physics signatures that different corners of the landscape predict. And it can measure with increasing precision the low energy parameters, the coupling constants, the particle masses, the Higgs vacuum expectation value that determine which corner of the landscape we occupy. If the standard model parameters really are environmentally selected from a landscape, we would expect them to have values near the boundaries of the regions where life is possible. The Higgs mass being in the metastable range, the cosmological constant being small but non-zero, the strong CP violation being apparently zero when it need not be, these could all be signs of environmental selection from a landscape, or they could be signs of a deeper underlying principle, a symmetry or a dynamical mechanism that forces these values. Distinguishing between these interpretations is one of the central challenges of 21st century physics. What makes this challenge so interesting is that it is not entirely philosophical. Concrete theoretical predictions depend on which interpretation is correct. If the Higgs mass is stabilized by a new symmetry like supersymmetry, the LHC should eventually find the superpartner particles. If it is stabilized by new strong dynamics, the LHC should find signs of new composite states at the TV scale. If it is environmentally selected from a landscape with no new symmetry, then neither of these signatures would appear, and the LHC would find nothing beyond the standard model at accessible energies, a result that would itself be deeply informative, if deeply disappointing. The absence of new physics beyond the Higgs boson at the LHC is consistent with the landscape interpretation, but is also consistent with new physics lying just beyond the machine's reach, waiting for a more powerful successor to find it. The history of physics includes many examples of symmetries and principles that were not recognized until the right question was asked in the right way. The next breakthrough may require a question that nobody has yet learned how to ask. What is certain is that the edge of observation is not fixed. It moves with every new instrument, every new technique, every new theoretical insight that reveals a new way to extract information from accessible observations about inaccessible regimes. The LHC has pushed the edge. Future machines will push it further. The cosmic surveys being planned will push it from the cosmological direction. And somewhere in the territory that these approaches are mapping, carefully and patiently and from multiple directions at once, the answers to the deepest open questions in physics are waiting to be found.